Okay, so we are going to recall something that we've learned before and apply it to our next concept that we want to learn from electric fields over here. So we know that if I have some mass and I lift it above the surface of the earth, which is basically the ground, and if I lift it above at some height, I can say that the potential energy that the mass has gained in moving above the ground is given by mgh. We all know this, right? But in order to get the mass off the ground, we need to do some work on the mass. Therefore, I can say that this potential energy over here is actually the work done on the mass against the gravitational field, because that's what the gravitational field is doing. It's basically trying to attract the mass to itself. Okay, the mass of the Earth and the mass of this object over here. So we can then rewrite this and say that work done is actually equal to mgh, and I can further extend this to say that this factor of gh here is actually equivalent to the work done per unit mass. You see, I've just flipped the mass over. Okay, so what is being said about this, or what this equation basically represents, is that it's saying that if there is some height difference, then this height difference is going to be proportional to the amount of work that I'm doing if I want to lift up a certain mass above the ground. The greater this height, the more work I have to do on that mass to lift it above the ground. Now, of course, once I cancel out the force lifting it up, then it'll just fall back down, and all this potential energy is going to revert back to kinetic energy, right? So we have this kind of energy transformation over here. So what I'm going to do now is I'm going to use this example. I'm going to translate this concept to electrical fields. So say, for example, now I have two parallel plates. Okay, let me just remove that. Okay, hold on. And get another color here. Okay, so let's just say I have two electrical plates. A positive plate on the top, positively charged plate, and I have another plate parallel to it, and it is at the bottom here, and it's negatively charged. Okay, so what's going to happen is I'm going to get an electrical field, and this electrical field is going to move from the positive plate to the negative plate. We all know this from previously, right? So we get this uniform electric field, right, downwards like this. Oh, downwards. Okay, my lines are a bit crooked, but you get it. This is a uniform electrical field. And let's just say I were to place some amount of charge in between these plates. Let's say I put a positive charge right at the top here, very close to the positive plate. Now, we know that the positive charges will repel one another, and this positive charge is going to move along the direction of the electrical field towards the negative plate. Okay, once again, this is the electrical field, and this here is a charge which I'll call Q. Okay, so what we're trying to establish here is that in the same way as with the gravitational field, I had this height difference and there was work done per unit mass, I also now have, in this case, a charge difference between the plates. And hence, what we have here is a potential difference. So we're going to say that there is this difference here, which in the electrical field sense is called a potential difference, which we denote as delta V. So let's put it down. It's potential difference because we have this difference in charges. Okay, so now this is going to equal to the work done by the electric field on the charge to move it across the plates. So there is work done here, but this work done is not on mass, because mass is for the gravitational field. We have instead here charge. So this is work done over charge. Okay, and there we go. We have this relationship, which is very similar to that of my gravitational field, but in this case it's for the electrical field. So the potential difference here is equal to the work done per unit charge. So over here, if I have a positive charge, it's going to repel away from the positive plate to the negative plate, and hence it has potential, which is now being translated into kinetic energy. But if, let's say, I had my positive charge over here instead, on the starting at the negative plate, then if I want to move it back towards the positive plate this way against the field, then I would have to do work on the charge to move it against the field. Whereas in the first case, the electric field is the one doing the work on the charge. In this case, I'm doing the work if I want to push it back against it. So if I'm pushing it back against it, it will gain potential energy. In this case, the one before, it was being pushed by the electric field, so all the potential energy here is being translated into kinetic energy. Whereas over here, I'm basically giving it kinetic energy, and it is being translated back into potential energy. In the same way, of course, we can also look at negative charges, and if I have a negative charge here, then the work will be done on the charge by the electric field, moving it in the direction of towards the positive plate. So in this case, again, you are moving from a place of potential energy and you're gaining kinetic energy. But if the negative charge started here instead, then you would need to do work on the charge against the electric field to push it the other way, because the negative charge doesn't want to go to the negative plate. It wants to stay at the positive plate. So in this case, we have kinetic energy being provided to the negative charge in order to push it against the field, and it gains potential energy. In any case, this shows that there is work done per unit charge, and that shows that you have some amount of potential difference.